So we're going to talk about linearity of expectation, which is a pretty important concept that you'll apply throughout the class. And in order to prove linearity of expectation, at least for the proof that we're going to give under certain conditions, we need some technical tools, and one of them is going to be Fubini's theorem. So Fubini's theorem gives some conditions for when we can switch the order of sums or integrals. So we want to know when we can switch. So let's say we have the integral over x and then the integral over y of f of xy dy dx. So this is a multivariate function of x and y. And we want to say that this is equal actually to the integral over y and then the integral over x of f of xy dx dy. So you see that we switch the order of integration here. And this is actually true if any of these three conditions are true. So we're going to ignore this first one. But if any of these conditions are true, so the only difference is we've actually replaced the f of xy to absolute value of f of x and y. So it's actually easy to see that if f of xy is positive, then absolute value of f of xy is the same as f of xy. So Fubini's theorem holds immediately. That's something called Tonelli's theorem. Or lemma, not quite sure. And to prove linearity of expectation, we're going to use some properties of sums and intervals. These are pretty general, so you've probably seen this and probably Fubini's theorem in your calculus class. But if you haven't, I'm not going to explain this, but you should just look over this. So linearity of expectation. Suppose x and y are two, let's say they're continuous random variables just for simplicity, but it can be any random variables. Let's say x has this density f of x, and y has density f y of y. And let's say they have a joint density f of xy. And let's suppose that we have some constants in the real line. Then we have expectation of ax plus by is equal to a times expectation of x plus b times ey. If e of x is less than infinity and e of y is less than infinity in absolute value, right? So linearity of expectation actually holds for more general conditions, but for this proof, we're just going to assume these conditions here so that we can apply Fubini's theorem. So first, let's prove this pretty basic statement. Expectation of ax is equal to a times expectation of x. So by definition of expectation, this is actually just the integral over the sample space of x of a times f of x dx. Right, and by using the property of linearity of integration, we can pull out this constant a outside, like we did here, and we're left with a times this integral. But this integral is the integral over the density function, which integrates to 1. So this is just a times 1, which is a. So now let's show that expectation of the sum is actually just the sum of the expectations. So this is the second part of linearity. So let's apply the definition of expectation to this, right, to x plus y. So this by definition, and then if Fubini's hold, then we can actually break this integral into the integral over x, the sample space of x, and the integral over y, all possible values of y, and then x plus y, f of xy, xy, dy, dx. So note that we actually can't break this joint density down so we can't say f of xy is equal to f of x times f of y, f of x, and f of y, because we don't know that they're independent. So linearity of expectation actually holds even if the random variables are not independent. So this is really important. So here we're just going to use the distributed property, and then like so. And to go to this line, we're just going to use the linearity property to break this integrand into the integral of this entire thing into 1 over this, and then another part here, right? So this, we broke it into 2 integrals. And then now, note that this x is a constant with respect to y, so we can pull it out by linearity of integration. And then by Fubini's again, we're going to switch the order of integration here from dy dx to dx dy, right? And then notice here, so now that we switched it to dx dy, notice that y is a constant with respect to x, so we can pull out this constant. So let me explain what's going on here. Note that we have the joint density, but what happens if we integrate the joint density over the entire space of y with respect to y? That's just the definition of the marginal of x, which gives us f of x. So we have integral over the entire space of x times f of x dx, plus by a similar method of what we did over here, we can reduce this to the marginal of y. But note that these two things, this is the definition of expectation of x, this is the definition of e of y. So we proved the claim. Now to finally prove the statement that we had in above, we can break by linearity of so we can break by linearity of expectation of ax plus by. We can break it into e of ax plus e of by what we just showed above here, right? So we just defined a new random variable ax and a new random variable by, and then break that expectation into 2 expectations. And then we applied the linearity property where we can pull out the constant, and then over here too. So this e of ax becomes a times e of x plus b times e of y.